Hi, welcome to lecture 9.3 covering double angle, half angle, and reduction formulas. So what this section is going to cover is taking the sum and difference formulas that we're already familiar with and using those to derive how to go about taking the sine or cosine or tangent of angles that are added, as well as subtracted. So or halved or doubled. So that's what we're going to move through. Let's go ahead and get started. Okay, so the first thing we're going to talk about this evening is double angle formulas. Oops, LE, there we go. And this is the special case of the sum formulas for sine and cosine. And the reason this is considered a special case is because this is when your angles are equal to each other. So I'm just going to show you how we go about getting these formulas. They're not, these, deriving these formulas are not difficult at all. So here you can see I'm starting out with just the regular sine sum formula, and I've gotten it written over to the side, to the right-hand side there, showing what it equals. And to turn this into what we consider a double angle formula, we're going to let alpha, which equals beta, we're going to let those equal one angle. We're going to give them a common name since they are, we're setting up the premise that they are the same angle. So that would mean we actually have the sine of theta plus theta there. And then we just change our angles on the other side to thetas. So sine theta, cosine theta, plus cosine theta, sine theta. And then from there, you can see that, let me get a different color. These terms are the same terms. They're like terms. It's okay that the sine and the cosine are flip-flop because multiplication is commutative. So what we end up getting is that the sine of 2 theta, so an angle that's been doubled, the sine of 2 theta is equal to 2 times sine theta cosine theta. And that is our double angle formula for sine right there. So like I said, not too difficult to arrive at that conclusion. Same thing with the cosine alpha plus beta. We're once again going to start with the premise that these angles are equal to each other so that we end up doubling that angle. So I'm just going to replace all my alphas and betas with thetas. Cosine theta plus theta equals cosine theta, cosine theta, cosine, minus sine theta, sine theta. Well, we know when we multiply something by itself, that is simply squaring it. So we get that the cosine of a double angle is the same thing as cosine squared theta minus sine squared theta. And that is our cosine double angle formula. Okay, moving further, your textbook says, okay, we can expand our ideas of these double angle formulas and look at them in different forms because they may show up in different manners with the different problems that you may be working with, especially when you're verifying that one side of equation actually does equal the other side. You're going to see these show up in various forms. So the first thing that we'll notice is that we have, let me get a different color. Right here, I can replace cosine squared theta. And I can replace that using my Pythagorean identity. So I'm going to put that in green so that you can see that that's what I replaced. That is also known as 1 minus sine squared theta. And like I said, that just comes from our Pythagorean identity. And then we're subtracting sine squared theta. So what we have happening here is, well, first let me get rid of the parentheses. There's an understood 1 there that distributes. And so this is 1 minus sine squared theta minus sine squared theta. And those sine squared theta terms are understood to be -1 of those things. So I can combine my like terms with this one as well. And I get 1 minus 2 sine squared thetas. Easy enough. And then finally on this page, we have cosine of 2 theta. We're going to start with the same premise, cosine squared theta minus sine squared theta, but this time we're going to replace sine squared theta with 1 minus cosine squared theta, so that everything's looking like cosine in this one. So I have, sorry, I'm switching between colors with pens a lot. So I have cosine squared theta minus, and I can call sine squared theta 1 minus cosine squared theta. Once again, that's just from the Pythagorean identity. And I also have that understood -1 that needs to get distributed. And I end up with cosine squared, oh, that's a theta right there, theta minus 1 plus cosine squared theta. So here we get 2 cosine squared theta minus 1. And then we've got tangent to look at, and then we'll actually use these for a moment with some examples. Good so far, Katie? I see you're typing something. Yeah, this is not hard at all. And actually, what you have to know to move through this section is your algebra skills. I think there may be one problem. Actually, I think it's a 9.4 because I've been working on 9.4 as well today. There might be one problem that you have to go to the unit circle to get a value. But other than that, it's all algebraic and knowing how to manipulate expressions algebraically. Oops. Okay, so now we have the tangent of alpha plus beta, and we're going to start with that premise that alpha plus beta equals theta. That alpha equals beta equals theta. So that's the first thing I'm going to do is just replace all of my alphas and betas with thetas. Tangent theta plus theta equals tangent theta plus tangent theta divided by 1 minus tangent theta tangent theta. Okay, so I have like terms in the numerator. I can call that 2 tangent thetas. And in the denominator, I have 1 minus tangent squared theta. And that's your identity. So we have, oh, let me write tangent of 2 theta. So we have the tangent of 2 theta equal to that right side right there. Okay, let's look at some problems that use these formulas. So we have them right there at the top for us. And notice we have the cosine in all forms there. Okay, so this first example says the sine of theta is equal to 5/8. Theta lives in quadrant 1. So just a quick picture of that. And we have theta living in quadrant 1. And then it says find the cosine of, I'm sorry, I'm saying theta. The sine of alpha lives in quadrant 1. So find the cosine of 2 alpha. And I think they must have meant an alpha right there as well. I think they just got some misprint. Okay, so let's think about this before we move into it. Cosine in quadrant 1. Remember, the coordinates of any point in quadrant 1 is a positive x and a positive y. And we know x as cosine theta and y as sine theta. So cosine in quadrant 1 is going to be positive. So when we get to the end, we should have some positive value. All right. So we have the cosine of 2 alpha. Now, I'm given the sine of alpha. I have a value for that. So I have chosen to use this version of the cosine double angle formula because it's got sine in it and I don't have to do any work. I don't have, well, I mean, I have to do some work, but I don't have to know what cosine is to use that particular version of the cosine double angle formula. So this is equal to 1 minus 2 sine squared alpha. Well, I know what the sine of alpha is. So I can come in here and say this is the same thing as 1 minus 2 times 5/8 squared. All right, when I square a fraction, I square my numerator, square my denominator. So this is 1 minus 2 times 25/64. And I can divide out a common factor of 2 right here. 2 goes into 2 once, and 2 goes into 64 32 times. And I can create a common denominator between my terms by multiplying 1 in the form of 32 over 32 with that 1 at the beginning as that first term. So what I have now is 32 over 32 minus 25 over 32. Well, now I'm ready to combine my numerators over my common denominator. And then 32 minus 25 is 7/32. Now the only thing that I want to go back and double check is, okay, did I end up with a positive value? Because if I didn't, then I need to make it a positive value because cosine is positive in the first quadrant. Is that okay for you, Katie? Yep, just simple algebra. And this next one is even easier. Yeah, this whole chapter's kind of felt like a breath of fresh air. After that graphing chapter we went through with graphing all of the trig functions, that one's a little brutal to make it through. Okay, so here we have the cosine to the fourth power of theta minus sine to the fourth power of theta. Now, I say that this one's easier, but you gotta be clever with this one. You have to recognize that this right here is a difference of squares. And just as a quick factoring recap, whenever you have something squared minus b, something squared, that always factors as a plus b times a minus b. So I just want to show that this thing is actually equal to the cosine of 2 theta. So the first thing I'm going to do is factor that. So this is cosine squared theta plus sine squared theta times cosine squared theta minus sine squared theta. And I tell you, the thing that clued me in when I ran across this particular problem is it was raised to the fourth power. And I have not seen any of our formulas have something raised to the fourth power in it. So my first thought was, oh, I've got to factor this. I looked at it a little bit closer. I'm like, oh, okay, that's the difference of squares. Very easy to factor. Now we have expressions for each of these things here. So from our Pythagorean identity, we know that cosine squared theta plus sine squared theta, that's just equal to 1. And that's way back when we studied the Pythagorean identity. That comes from the Pythagorean triangle, x squared plus y squared equal, or a squared plus b squared equals c squared, that type of thing. X squared plus y squared equals 1 if it's on your unit circle. And then we input our cosine and our sine for our x and our y. Now, the second factor is not the Pythagorean identity because it's subtracted. However, if you look right up here, cosine squared theta minus sine squared theta is equal to cosine of 2 theta. One times the cosine of 2 theta is just cosine 2 theta. Verified. That's all we had to do. So the real clever part of this one was that you had to pick up on the fact that that was a difference of squares, and you had to recognize that this factor right here is the Pythagorean identity. So not bad, but just a little cleverness that's needed. Okay, moving along to power reduction formulas. Oh, no, we had one more on that page. I'm sorry. Lagging back by itself. And this one's not bad either. So we start out with cosine 2 theta times cosine theta. And we're trying to show that that is the equivalent of cosine cubed theta minus cosine theta times sine squared theta. So what I did here was I used this identity. The cosine of 2 theta is cosine squared theta minus sine squared theta. So I replaced, let me color code, I replaced cosine of 2 theta with cosine squared theta minus sine squared theta. And I'm multiplying that by cosine theta. Well, simple distribution gets us exactly where we need to go, because we are trying to show that this thing is equal to cosine cubed theta minus cosine theta sine squared theta. That's it. I don't want to jinx us, Katie, and say we might finish early tonight, so I'm not going to. But I'm feeling it, just so you know. Okay, so power reduction formulas. And it's tough to see, but this is a sine squared theta and a cosine squared theta. So what these particular formulas do is take an expression of sine or cosine that may be squared or have some other power besides 1, and break it down into only having powers of 1. Okay, so we'll start with this form of the cosine double angle formula that we showed on the last page, and I'm just going to solve for sine squared theta to show what that thing is equal to. So once again, good old algebra skills here. I'm going to subtract 1 from both sides, and that gives me cosine of 2 theta minus 1 equals negative 2 sine squared theta, and then I just divide both sides by negative 2. And we have, okay, this is one thing that was a little tricky that they did. They divided the negative out here, and so that causes that cosine to become negative, and they flip-flop those terms to have the constant first to come before the cosine term. So, I'm trying to grab my pen pad here. All right, so when I do all that business all in one step, I end up with a positive 1 minus cosine 2 theta divided by 2. And that equals sine squared theta. So this takes sine squared theta, which is obviously a power of 2, and it turns it into something that is only raised to the first power. That's why this is called power reduction formulas. Okay, same thing here, except now we're going to solve for cosine squared theta to see what we can call that. So we add 1 to both sides, and I have cosine 2 theta plus 1 equals 2 cosine squared theta. And then I just divide by 2. Simple enough. And I get that the cosine squared of theta is equal to cosine 2 theta plus 1 over 2. And of course it could be 1 plus cosine 2 theta over 2. All right. And then we have tangent as well. We know that the tangent is the sine over the cosine. So I'm going to substitute for sine squared theta. I'm going to use my Pythagorean. Actually, I'm not going to use my Pythagorean identity. I'm going to use the power reduction formula that I just came up with and replace that with 1 minus cosine 2 theta over 2. And I'm going to replace cosine squared theta with 1 plus cosine of 2 theta over 2. Okay, so this looks really nasty to begin with, but it's not bad at all. So my sine squared theta is 1 minus cosine 2 theta over 2, and that's big divided by 1 plus cosine 2 theta over 2. Well, I never divide fractions, I multiply by the reciprocal. So 1 minus cosine 2 theta over 2 times the reciprocal 2 over 1 plus cosine 2 theta. My 2's divide out, and I end up with tangent squared theta equaling 1 minus cosine 2 theta divided by 1 plus cosine 2 theta. That's it. Now let's use them. Okay, so this one's a little long. Hopefully I'll be able to cram it all onto this small slide page. Okay, so we start out with the cosine to the 4th of x. And it says to write an equivalent expression that only involves sine or cosine and no powers are greater than 1. So the first thing that I did was split this into cosine squared x times cosine squared x, because I knew I had expressions for those. So my cosine squared x is the same thing as 1 plus the cosine of 2x divided by 2, and I'm multiplying that by 1 plus the cosine of 2x divided by 2. Okay, so this is distribution that needs to happen in my numerators. We multiply fractions straight across, so I go there, 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 and there, and then I just multiply my 2's straight across in the denominator. So 1 times 1 is 1. 1 times the cosine of 2x is positive cosine 2x. Cosine of 2x times 1 is positive cosine 2x. Cosine of 2x times cosine of 2x is positive cosine squared of 2x. And that's all being divided by 4. Now I have like terms here that I can bring together. You're not done yet because of this 2 sitting right there. Remember, we don't want any powers greater than 1, so we've still got more work to do with this one. So this is equivalent to 1 plus 2 cosine of 2x plus cosine squared 2x divided by 4. Now I need to focus on this cosine squared of 2x. Okay, so I'm just going to rewrite everything. 1 plus 2 cosine of 2x plus, okay, let me grab my purple pen again. This is the same thing as 1 plus the cosine of 2 times 2x, because now our thing that's sitting in the position of theta is a 2x. So we've got to double it again. Does that make sense, Katie? Okay, good. And then that's over 2. And then I'm going to divide that whole thing by 4. Okay, so I have to get, I can either get common denominators and add my numerators, but I think it's easier to go ahead and pull off that 1/4 out front and just multiply what I have left over here. So my next step looks like this. 1/4 plus, okay, so 2/4, so I'm looking at this second term here, that's the same thing as 1/2 cosine of 2x. So I'm just dividing each of those by 4. And then this last one, I haven't understood, let me just point this out. I haven't understood 1/4 that multiplies with that whole thing. So plus 1/4 times 1 plus cosine of, and I'm going to go ahead and call this 4x over 2. Okay, we're getting there, I promise. So this is 1/4 plus 1/2 cosine 2x. Okay, now I'm gonna multiply. No, I'm sorry. Yeah, I'm gonna pull that 1/2 out front. So plus this is 1/4 times 1/2, and then that's just now multiplied by what's in the numerator, 1 plus cosine 4x. Okay, so I've got to come up over here to finish. Equals, all right, 1/4 plus 1/2 cosine 2x. 1/4 plus 1/2 is, I'm sorry, times 1/2 is 1/8. And that's 1/8 times 1 plus the cosine of 4x. I'll give brackets there. Okay, now if I distribute that 1/8, I have oh, did I put plus and it was supposed to be minus? Or did I mess it? Hang on just a second, I'm talking to myself. Let me pause the recording real quick because I think I made a sign error on my page. Okay, so here we have 1/4 plus 1/2 cosine 2x, and now I'm going to distribute that 1/8, so I have plus 1/8 plus 1/8 cosine 4x. All right, so this is the first time I've gotten rid of all my parentheses and everything is raised to the power of 1. So now I just need to add my fractions together. So I've got a 1/4 that's going to be added to the 1/8. And then I have plus 1/2 cosine 2x plus 1/8 cosine 4x. Okay, so to add 1/4 and 1/8, I need to multiply by my clever 1 in the form of 2/2. And so I have 2/8 plus 1/8 plus 1/2 cosine 2x. This is the most lengthy problem we're going to do tonight, by the way. Plus 1/8 cosine 4x. All right, 1/8 and 2/8 make 3/8 plus 1/2 cosine 2x plus 1/8 cosine 4x. And that's it. That is a nasty, not feel good answer, but that's it. And I did double check the book, and we are correct. As long as the book's correct, we're correct. The book has had a few mistakes in it, but not too many. Katie, I see you're typing something, so I'm going to wait to see what you have to say. Should we write it with the numerator all over 8? You would have to, if you did that, I mean, it's okay to do that if you want to, but notice we have a 1/2 here. So you'd have to multiply that by 4/4 to be able to write all that over the common denominator of 8. This is how the book left it, but it certainly should not count it wrong if you did modify that to all have a denominator of 8. That's a good question, though. It makes you think it looks prettier. I know, that is a nasty looking answer, though. All right, let's go ahead and move forward. Okay, so now we have, and this is going to be a quick one. Notice there's not much space there, so that's a good sign. When you get to a problem, there's not much space to work it, you know it's not going to be too bad. All right, so sine cubed of 2x, and we're trying to show that that thing equals this nastiness out to the right side. So I'm going to start by splitting up my sine cubed into sine 2x times sine squared 2x, because I know I can work with both of those. So this is the same thing as the sine of 2x times sine squared of 2x. And I'm just going to leave my sine 2x, because notice I have a sine of 2x sitting there, so I really don't want that to go anywhere. So sine 2x times, okay, now I'm going to change sine squared of 2x using my power reduction formula. So this is the same thing as 1 minus the cosine. Remember, you got to double that theta there in the formula. So this is 2 times 2x, just like we did in that last one, and it's divided by 2. So I have the fraction understood 1/2 that can come out front. Because remember, I'm trying to get that 1/2 out front there. So I'm going to factor that 1/2 out and put it up front. This is 1/2. And that's 1/2 times sine 2x, and I'm multiplying that by my numerator now. 1 minus cosine 4x. And that's exactly what we were trying to show. Done. Those are the nice ones. Okay, this is another lengthy one, so I did lie. This truly is the only other one that takes, you know, some real time to get through. And I think I did jinx us, Katie, because we've only got 15 minutes to get through the rest of this. And I don't know what's going to happen. Okay, so we're trying to show that 10 cosine to the 4th x is equal to all this thing on the right-hand side. So once again, I'm going to start by just splitting that cosine to the 4th of x. So this is 10 times cosine squared x times cosine squared x, because I know I've got expressions for cosine squared x. So this is the same thing as 10 times, this is cosine 2x plus 1 over 2 times cosine 2x plus 1 over 2. I've got distribution to do in the numerator, so I'm going to multiply here, 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 and here, and then I'll just multiply my denominator straight across. So this is 10 times, oops, I didn't mean to still have my blue pen, 10 times, okay, cosine of 2x times cosine of 2x is cosine squared 2x. Cosine 2x times 1 is just positive cosine 2x. 1 times cosine 2x is positive cosine 2x. And 1 times 1 is 1. And that's all over 4. So I can divide here. 2 goes into 4 twice, and 2 goes into 10 5 times, and I can pull that 5 halves out front. So this is the same thing as 5 halves times the numerator there. So I'll combine my like terms in the center. Cosine squared 2x plus 2 cosine 2x plus 1. Okay? Now, now I have a new cosine squared 2x sitting in there. So I've got to reduce this power right here. And I'm going to use the same technique that I used up there, but don't forget that because I've already got 2x, I've got to double it. So it's going to show up as that 4x again. Okay, so 5 halves times, let me give myself brackets to work in here, 1 plus the cosine of 2 times 2x, so I'm doubling that, divided by 2, plus 2 cosine 2x, and I'm going to go ahead and say that's over 1, and you'll see why. I'm sure you already know why, plus 1 over 1. I did that because I need to get a common denominator to be able to add all of those fractions together. So I'm going to come back and I'm going to say, well, I need to multiply this by 2 over 2 and this as well by 2 over 2. 5 halves times 1 plus cosine of 4x over 2 plus, now I've got 4 cosine 2x over 2 plus 2 over 2. And I can combine my numerators over my common denominator. So 5/2 times 1 plus cosine 4x plus 4 cosine 2x plus 2 all over 2. And I'm going to have to come up here to finish. Okay, so I'm going to pull that 1/2 off so that I just have my numerator inside my brackets. So this is 5/2 times the 1/2 that I'm pulling off now. And now that's going to be multiplied by 1 plus cosine 4x plus 4 cosine 2x plus 2. Oh, I didn't even see. These snuck by me. I can combine my 1 and my 2 right there. And I'll go ahead and multiply those fractions out front. So this is 5/4 times 3 plus cosine 4x plus 4 cosine 2x. Following so far, Katie? We're getting there. We're getting there. Okay, great. Okay, so now I'm just going to distribute to each of my terms here. And that's a 3/1 right there. So that first term is 15/4 plus 5/4 cosine 4x. And notice my 4's divide out there. So I just have plus 5 cosine 2x. And believe it or not, we finally made it to showing that that is equivalent. Yay, I know. I feel like I deserve a trophy or something. Once again, they're not difficult, but that one was just tedious, just absolutely tedious. Okay, we've got half angle formulas to look at, and then we will be out of here. So, half angle. Now, we're going to derive these first, and then I'm going to go back up to that paragraph at the top and point some things out to you. Okay, so what we're going to do to figure out half angles is we're going to let theta be equal to alpha over 2. So that's what I'm going to do first, is just replace my thetas with alpha over 2. So I have sine squared of alpha over 2 equaling 1 minus cosine of 2 times alpha over 2, all divided by 2. So inside that cosine there, my 2's divide out. So that just becomes cosine alpha. So I've got sine squared alpha over 2 equals 1 minus cosine alpha over 2. But I don't want to know what the sine squared of alpha over 2 is. I want to know what the sine of alpha over 2 is. So I need to take the square root of both sides. And I get the sine of alpha over 2, so a half angle there, is equal to the positive or negative square root of 1 minus cosine alpha over 2. Now, let me point you back up to this paragraph. It says, note that the half angle formulas are preceded by a positive negative sign. This does not mean that both the positive and the negative expressions are valid, like if we were solving a regular equation. Rather, it depends on which quadrant. Oh, that should say alpha over 2. I missed that when I was fixing the formatting. Alpha over 2 terminates. So you've got to pay attention to what quadrant when you're actually using these formulas to figure out, okay, should I be taking the positive or the negative value of this? And the same thing is going to be true with the cosine squared of theta over to the right here. So we're going to let the same premise stand for this cosine squared theta here. We're going to call theta alpha over 2. So we start out with cosine squared of alpha over 2 equal to 1 plus the cosine of 2 times alpha over 2 divided by 2. My 2's divide out there, so I've got cosine squared alpha over 2 equal to 1 plus cosine alpha over 2. Take the square root of both sides. And I get cosine alpha over 2 equal to the positive or negative square root of 1 plus cosine alpha over 2. Okay, so those are my half angle formulas for sine and cosine, and now we're going to look at tangent real quick. Okay, so we start out with the identities here, or the formulas here, and notice we have tangent squared theta, so we want to figure out what tangent of alpha over 2 is. So theta, we're going to let that be alpha over 2. So tangent squared alpha over 2 equal to 1 minus cosine 2 times alpha over 2 divided by 1 plus cosine 2 times alpha over 2. My 2's divide out, and I have that tangent squared of alpha over 2 is equal to 1 minus cosine alpha over 1 plus cosine alpha. I don't want to know what tangent squared is, though. I want to know what tangent is. And I end up with the tangent squared of alpha over 2 equal to positive or negative square root of 1 minus cosine alpha divided by 1 plus cosine alpha. Now, they give you this formula 2 other ways. I'm going to show you how they derived one of them. And you use the same technique, same type of technique to get the other one. What they tell you, and I've got it on the next page for us, is that this whole thing not only equals this big thing right here. Oh, that shouldn't have a square on it. I'm sorry. We took the square root. Okay. It not only equals that whole thing, but it can also be equal to sine alpha over 1 plus cosine alpha, or it can be equal to 1 minus cosine alpha over sine alpha. And I'll show you how they got one of those. Like I said, the process for the other one is the same. So if we start out with the square root of 1 minus cosine alpha over 1 plus cosine alpha. That's the same thing as the square root of 1 minus cosine alpha divided by the square root of 1 plus cosine alpha. Remember, we can't have roots in the denominator, so if I rationalize that denominator, I multiply by 1 in the form of square root of my denominator there, 1 plus cosine alpha divided by square root of 1 plus cosine alpha. So that's just 1 that I'm multiplying by there. And when I multiply square roots, I actually multiply what's under the root. So this is equal to the square root of 1 minus cosine alpha times 1 plus cosine alpha. I've got a difference of squares right there. And in the denominator, I've got the square root of 1 plus cosine alpha, but that thing's squared because I'm multiplying it by itself. Whenever you take the square root of something squared, it goes away. So what I have equal to the square root of 1 minus cosine squared alpha. I just changed my 1 plus cosine alpha, 1 minus cosine alpha back into its difference of squares form. Was that too much of a leap without showing that distribution, Katie? Because I can go back and show the distribution if I need to. Okay, cool. And then down in the bottom, all I have left is 1 plus cosine alpha. Okay, so now here's a little bit of trickiness. 1 minus cosine squared alpha is the same thing as sine squared alpha. That's your Pythagorean identity over 1 plus cosine alpha, and when I take the square root of something squared, I'm just left with that thing, sine alpha over 1 plus cosine alpha, and that's that one right there. And you work with the other one the same way. The only difference is instead of rationalizing the denominator, you work at rationalizing the numerator, and you get the opposite one. Is that good, Katie? That make sense? Okay, great. So let's use these and then we'll be done. Okay, so we are given, and I'll write this a little bit bigger, the tangent of alpha is equal to 8 over 15. Well, all of these formulas that I have, they all deal in sine and cosine, and they're asking me to find the sine, the cosine, and the tangent of the half angle. But all I have is that the tangent of the actual angle is 8/15. So what I need to do is use a right triangle to figure out what the sine and the cosine is. So we know that theta lies in quadrant 3, which means since alpha lies in quadrant 3, that means that 180 degrees has to be less than alpha, has to be less than 270 degrees, because that puts it into quadrant 3. Which also means that if I half everything, I know where my half angle lives, because I need to know what sign to take. So 180 over 2 has got to be less than alpha over 2, has got to be less than 270 over 2, which means 90 has got to be less than alpha over 2, has got to be less than 135. So what this means is alpha over 2 lives in quadrant 2. So sine in quadrant 2 is positive. Cosine in quadrant 2 is negative, and tangent in quadrant 2 is also negative. So we've already determined what sign we need to take once we figure that out. Katie, I see you're typing, so I'm going to wait to see what you have to say about that. It's okay. So what it says is that alpha is in quadrant 3. We want to know where half alpha, okay, so if alpha is in quadrant 3, that's between 180 and 270. But we're working with alpha over 2. So alpha over 2 actually lives in quadrant 2. Okay, good. All right, so let's get to figuring out what the sine and the cosine are value-wise, and then we can basically, once we get the sine and the cosine of alpha, it's just a bunch of working with fractions. Okay, so if we have our alpha in quadrant 3, we're looking at a triangle like this. This is our alpha, not our alpha over 2, but our alpha. So alpha lives right here. And I know that tangent is opposite over adjacent. So I have opposite over adjacent. But in quadrant 3, this had to be negative because it went to the left. And in quadrant 3, this also has to be negative because it went down. And so I'm just going to use my Pythagorean theorem to figure out what the hypotenuse is. So I have negative 15 squared plus negative 8 squared equals my hypotenuse squared. And that is 225 plus 64 equals c squared, so that's 289 equals c squared, and when I take the square root of both sides, I get that c is equal to 17. So my hypotenuse is 17, which means that the sine of alpha is equal to, okay, sine is opposite over hypotenuse, so sine is negative 8/17. And cosine is adjacent over hypotenuse, so that's negative 15/17. So now I've got expressions for sine, cosine, and tangent of of alpha, not half alpha. I'm going to use my formulas to figure out half alpha or alpha over 2. So let's start with sine of alpha over 2. Okay, my formula up here at the top says, well, that's equal to the positive or the negative square root of 1 minus cosine alpha divided by 2. However, I know that sine is going to be positive in the second quadrant, so we'll just take the positive from the very beginning. So this is equal to the square root of 1 minus, we know what the cosine alpha is. it's negative 15/17. And that's all divided by 2. So this is why I said at the beginning, yeah, it's just working with fractions the rest of the way down once you get that first part set. Okay, so this is equal to the square root of 1 is the same thing as 17/17. And now I'm adding, since I have minus a negative, 15/17, and that's still divided by 2, and that's a big square root. The square root of, okay, so 15 plus 17 is 32/17, and that's divided by 2. I never divide fractions. I multiply by the reciprocal. So this is the square root of 32/17 times the reciprocal 1/2. I can divide out my common factor of 2. So 2 goes into 2 one time. 2 goes into 32 16 times. So what I have here is the square root of 16/17, which is the same thing as the square root of 16 over the square root of 17, which is the same thing as 4 over the square root of 17. Can't leave that square root of 17 in the denominator. I need to rationalize it, so multiply by the square root of 17 over the square root of 17. And my final answer here is 4 square root 17 over 17. That is sine of alpha over 2, and it's positive because sine is positive in the second quadrant. All right. Now we have cosine. So the cosine of alpha over 2. And I'm just going to use my formula at the top there. I already know I need the negative of it because cosine is negative in quadrant 2. So this is negative square root of 1 plus cosine alpha. Cosine alpha is negative 15/17. That's over 2. So that is equal to negative square root of 17/17 minus 15/17 over 2, which is equal to negative 2/17 over 2. I never divide fractions. I multiply by the reciprocal. So 2/17 times reciprocal, 1/2. So that's negative, oh, my 2's divide out there. That'll make it even easier on me. So this is square root, a negative square root of 1/17, which is the same thing as negative square root 1 over square root 17, which is negative 1 over the square root of 17. Going to multiply to rationalize, so square root 17 over square root 17. And I get, this is negative square root 17 over 17. And finally, we have tangent. And I think for the sake of time, Katie, I'm going to stop after this problem. The last problem that I have on your sheet is just like these. You have to figure out what quadrant you need to be in. You got to draw a triangle, that type of thing. So I think we've beaten the dead horse enough here with going through each of these with this same set of information. Okay, cool. Okay, so tangent of alpha over 2 is equal to, okay, so I chose a different route than the book went with this. I chose a more simple version. I didn't want to deal with the square roots and all that stuff. So I chose the sine of A over, I think I chose the sine of A. Yeah, the sine of alpha over 1 plus the cosine of alpha. So the sine of alpha, here, I'll write it here, the sine of alpha over 1 plus cosine alpha. I wanted to make it easy on myself. Okay, so the sine of alpha is negative 8/17. And then I have 1 plus the cosine of alpha is negative 15/17. Okay, so that is negative 8/17 divided by 17/17 minus 15/17, which is negative 8/17 divided by 2/17. I never divide fractions. I multiply by the reciprocal, negative 8/17 times the reciprocal 17/2. My 17s divide out, and I end up with negative 4. And negative is correct because tangent is negative in the second quadrant. All right, that's where I'm stopping. Sorry I went over. Silly me to think that we were going to get done early. We were just flying through the first part so quickly. I got all excited. I knew I was